All right, here we're looking at this question. Two electrically conducting cylinders, X and Y, are made from the same material. Their dimensions are shown. The resistance between the ends of each cylinder is measured, and we want to know what is the ratio, the resistance of X to the resistance of Y. So the equation that sort of governs all of this is resistance is going to be equal to resistivity times the length divided by the cross-sectional area. Let's go through the language of the question again. They're electrically conducting. Okay, they're cylinders, which means they have a circular cross-section. So the area of the circle is pi r squared. They're made of the same material, which means they have the same resistivity rho. So that's the same. So we're going to be able to calculate the ratio of the resistances of X and Y by taking sort of a ratio of sort of these things for each one. So if X just has sort of a certain area based on its diameter and its length is just L, then the resistance of Y is going to be the ratio of these resistances is equal to the ratio of, this rho L over A. And so rho is going to be the same. L is going to be twice as long, so 2L. And then as we doubled the diameter, we doubled the radius, right? Doubling the diameter is the same thing as doubling the radius. But we have to think about how we double squared the area. In other words, there is 4 times the area in this circular cross section than there is here because the area goes as the square of the radius. And so we've got 4 times the area for Y here. If we think about this complex fraction as dividing a fraction, multiplying by the reciprocal, then the reciprocal of this down here is going to be 4A for Y over rho 2L. So I just kind of wrote these up here as the reciprocal because I'm doing this multiplication. Get rid of that now. All right, then what's going to happen here? It looks like these rows are going to cancel. These A's are going to cancel. These L's are going to cancel. All right, 4 over 2 or 2. 2 over 1. So A is correct. By doubling the length here, I've really made it more resistant. The resistance of this would be more resistant, but I've decreased the resistance by a greater amount by doubling the diameter. And so this has a bigger effect because of the sort of squared here. And that's why the resistance of this one is more. Again, by doubling the diameter, that has a greater effect in decreasing the resistance of this electrically conducting cylinder Y than doubling the length. And so doubling the length, again, just sort of thinking about resistance is rho L over A. And if all we do is double the length, then we've increased the resistance, right? But by increasing the area, we lower the resistance, right? When this number gets bigger and we don't change these, then this number goes down. So that's the key to making sense of question 30 here.